So far I've talked about so many things about poles and zeros, right? But for first order, remember first order there is only one pole, okay, one pole is over here. And then the further you are from the imaginary axis, okay, the slower, the faster you decay, okay, the faster you decay. If it's nearest to the imaginary axis, you're going slower, your decay is getting slower. So this is the key concept I want to make known because before I go to second order poles and zeros. Okay, so this is the second order. Similarly, this is the transfer function equation. Not similarly, but rather than similarly transfer function. Whatever. So this is the transfer function for second order. Okay, so as you can see, it's a little more complicated. Whatever thing that makes the equation poles is what? Whatever thing that makes the equation to infinity is called poles, right? So whatever thing in the denominator, we have to use quadratic equation. So when you use a quadratic equation, you will eventually get this equation over here. So S can be in terms of this thing, right? So therefore, if you were to sub in natural frequency, this is natural frequency, and this is the damping factor. Okay, if you were to sub in these two stuffs over here, you eventually get two poles. Okay, because you have two values. If you know quadratic equations, typically you will receive two values unless certain conditions. But nonetheless, if it's larger than 1, okay, if the damping factor is larger than 1, so in this case, if the damping factor is larger than 1, you will have two poles. That's called dominant pole. Dominant pole and non-dominant pole, the difference is what? Okay, the difference is that dominant pole will decay slower than, okay, so let's say this is the non-dominant pole. It decays very fast. For dominant pole, it decays kind of slowly, so you can say that dominant pole is, we have a term, okay, we call it a term, so you give me a minute while I find. Dominant pole can be said that when it is still somewhere, not zero, the other pole is already, decay finished already. You get what I mean? So yeah, the other pole is already gone. So in this case, at this point of time, okay, our maybe this red color, it's like already, maybe I should redraw the whole thing again. So it decay very fast down, and then the dominant pole should be like that. So at this point of time, the dominant pole is still decaying while the other pole is already, decayed. It's already go to zero. So we talk about, so dominant pole is this idea. And then before I dwell upon the other things, I want to make clear that whatever thing that makes the poles, okay, when we are looking for stability, look at the roots of the denominator. Whatever thing that makes the denominator zero, we will eventually know what is stable or unstable. So as we have already said earlier, okay, if it's lie on this side, it's considered stable. If it's on this side, it's unstable. So let me ask you, what is this? So is this pole stable? Is this two pole stable? Yes. Okay, it's because on this side. Okay. Anyway, so this is for when damping factor is equals to, or when damping factor is larger than 1. Okay. But what if it's equals to 1? When it's equals to 1, as you can see, actually didn't say that s, okay, the value of s, okay, which is in the real axis, okay, as I've mentioned, the graph itself, the real axis is in terms of s, okay. So value of s, you just plot it here, and then this is imaginary, okay. So the value of s can be also said that it is equals to the damping factor multiplied by the natural frequency. Okay, so this is one equation you may need to really go and understand. And then so this is why you actually write minus So hold on, it should be positive lah. I don't know, but yeah, you give me a minute. So before I continue, okay, I actually have a lot of trouble explaining this thing because I have little knowledge. So anyway, so if damping factor is above 1, okay, your value of S at this real axis is dependent on whatever thing you sub in over here. If it's equals to 1, okay, if it's equals to 1, you would know that since the equation state that this is the equation itself, okay, if it's equals to 1, this will become 0, and therefore this will become minus omega n, okay. And then if it's larger than 1, okay, based on this equation, based on this equation, you can actually have, you get what I mean. So everything, the S itself, you use this formula. So this is the holy formula you have to go and take down. This is the holy formula. I repeat, you're gonna take down. And the distance between these two poles is dependent on the distance. Is dependent on this equation. Okay, this is the equation. This is the portion over here. Okay, the difference between the two poles. So this is why if the damping factor is not equals to 1, okay, if it's not equals to 1, there will be a difference between two poles. But if this is 1, the distance between them are 0. This is why it explains two poles in one place, because as your damping factor, okay, it's kind of near to 1, okay, maybe it's 1.001 minus 1, okay, so it is moving. So imagine we have, hold on a while. So as we have seen, the distance between them is governed by this formula over here. Okay, so if it's larger than 1, okay, if our damping factor is larger than 1, let's say if this value, this whole damping factor square is equals to 1.12, okay, minus 1 times the natural frequency, you'll get some values in here. So the smaller you are, the closer you are towards this pole over here. Okay, and when you reach equals to 0, okay, when damping factor reaches equals to 0, you have two poles side by side. Okay, two of the poles are put together in one place. Now, what if the damping factor is less than 1? Okay, so if it's less than 1, you have a negative value. We call it negative a omega n. Okay, so this negative a is an imaginary axis. So you can still expand this thing into what do we call it, I. So this thing is actually minus a, if you remember. Okay, a dot with minus 1, this is I, is equals to minus a. So therefore, yeah, you get what I mean. So therefore, once you have a damping factor that is smaller than 1, you have an imaginary things, right? So therefore, you have a certain angle that is, going. So hold on. So you have a certain angle on the imaginary axis. Okay. So if your damping factor is so-called getting smaller and smaller, you're actually leaving the leaving the real axis more and more. Okay. So let's say we have this graph over here. Okay. Let's say your damping factor, okay, definitely is larger than 1. Smaller than 1. Okay. So as you, okay, maybe I should plot it out in terms of this thing. So when it's larger than 1, okay, this is the post. Okay, so if it's larger than 1, slowly going to equals to 1, they are going in this direction. Okay, they are going towards this direction. And when they reaches 1, they are both at the same point, right? should be at this point. And then when they are smaller than 1, they start to diverge. Okay, when let's say this is 0.99, okay, they are slightly over here. Okay, the angle itself, it's very small. Okay, so when the damping factor, okay, I should say this is square. And then when the damping factor square, which is getting actually anyway, the concept is that saying that the damping factor is smaller than 1. Okay, if it's getting smaller and smaller, let's say this is like 0.03, okay, which is much more than 1, it will actually be further away and the angle will be larger. So as you can see from the whole system itself, the poles is moving in this direction. Okay, maybe I should use a clearer color. This one. So they are moving in this direction. One going upwards and the other one going downwards. So they are moving in this direction, right? So this is somewhat I think with locus lah. Okay, but this is the concept that I want to convey. So I hope you get what I mean. And therefore another question before I end this video, okay, is that what if you want to plot, okay, for this thing, you want to plot the poles. How do you want to plot? Okay, these are the two equations. Okay. These are the few points you can take note. Okay, the theta is actually cosine theta equals to the damping factor. Since you know the damping factor, you can arc cosine this, you can get the degree itself. Okay, make sure radian is radian, degree is degree. I think it's safe, I think you can go with degree first. See how first and then go radian. Whatever. And then the omega natural frequency is the length itself, is the hypotenuse, and then this is the damping factor times natural frequency. Okay, so you know these two lengths, you can easily plot because they are always the same. Okay, they are conjugates of each other. If you say so. Okay, so this will be the part for poles and zeros for second order. Okay, and then hold on a while. To summarize, the transfer function is this, and then you take whatever denominator, okay, because whatever denominator will define whether your system is stable or unstable. So normally we work in the denominator group. So if also for this case we're quadratic, and therefore you do a quadratic equation, you'll get this form. And then for the position of the for the position of a poles itself, the distance and stuff like that is all dependent on your damping factor. Okay, damping factor change, and the trend itself, as you can see, is going in this direction. Okay, from the largest damping factor, the larger you are, the further your poles are. Okay, and it's going towards here. So as you can see, the further you are, then if you are further across here, then this will be unstable already. So I think so lah. So in the future, then we'll talk about how to deal with these things. And then next video, we'll talk about because we are still in the second order poles and zeros. So now we talk about the second order impulse and step responses. Okay, for this. And then next video we'll talk about that lah. And then perhaps we can talk about the overshoot. So next video we'll clear away all these things. Okay. And then next video we'll talk about this. So see ya.